In the next page here, we're going to formalize that a little bit and look at our steps for volume by cross sections. So these steps we're definitely going to practice with, but we'll just kind of write down for right now what our general outline will be. First thing that we're going to do is we are going to sketch the region that we're looking at. And if possible, if you can do it, making a little, even just a really crappy sketch of the three-dimensional solid can be handy, just to help yourself visualize what we're looking at here. Sketching the solid to whatever extent you can be useful. So make some sort of little sketch, at least graph the region that we're looking at, and we'll go through what that looks like. And also sometimes sketching a typical cross section can be useful too, or at least trying to visualize this in your mind. Okay, that way you know what we're looking at for the cross-sectional area, because that's the next thing you're going to find. Find A of X, the cross-sectional area. All right. And that leads you to your delta V, change in volume expression. Okay. Step 3 is going to be to find your limits of integration so that you can set up your integral. And that's where the sketches can come in really handy, because sometimes you can just look at the sketch and pick the limits right off of there. That's pretty nice. So once you have the cross-sectional area, that gives you the delta V expression, and you can integrate that cross-sectional area, A of X dx, like so. And so, yeah, that's going to be your last step. To find the volume, use our little expression right there, little equation, V equals A to B integral of A of X dx. All right. Now, for right now, notice how I am writing everything in terms of X. You can also do these in terms of Y. For those of you who watched the 5.6 videos on the areas between curves, if you got deep enough into those videos, you saw that we could do areas with respect to X, so integrating dx, or that we could do it with respect to Y and integrate things dy. So that is the same thing on these volume problems. You can do everything in terms of X, or you could do an integral, let's say from C to D, and then make everything in terms of Y in there instead. It's just about being consistent with your variables. Okay. And we'll do both cases here today with some problems, some with respect to X, some with respect to Y. So hopefully that'll help. Okay, so that's our overall procedure there, how we set up our integrals, that type of thing. So we're going to look at the types of solids that we're going to be focusing on here. Because there are a lot of different solids that you can use this process on. You can use this volumes by cross sections to do the volume of things with square bases, triangular bases, all sorts of good things. Like with those squares, there's kind of a fun shape you can make where the squares like rotate as the solid goes up in 3 dimensions. This is a horrible sketch, but anyway, the solid does something like that. Wow, that's pretty terrible, but if you can find a formula for the cross-sectional area, you can find the volume of any solid like that. But we are going to focus on a particular type of solid in this class called a solid of revolution. It's revolutionary. Well, what we're actually referring to is that the solid is created by using rotation or revolution. We are going to obtain these by rotating or revolving a given region about an axis or line. And for the sake of time, really, with our class this semester, we are just going to focus on rotating things about either the X or Y axis. You can rotate them about other lines, but it gets a little more involved. You can read through it in the book if you want, but just know that all I'm going to test you on is rotation about an axis. And that's all that's on your homework as well. Okay. And for these solids of revolution, when we do volume by cross sections, that gets called the disk method or the washer method. The difference between those two, because it really is kind of the same idea, is that the disk method is if you have a solid. So the cross sections are solid disks, like just like a penny, basically. Okay, there's nothing cut out of it. With the washer method, that's when your solid has a hole going through the middle of it. So it looks like a washer when you take the cross section. Okay, so washers are, you know, like the nuts, bolts, washers, that type of thing in construction. So there's a hole taken out of the middle of this one, like a big flat donut. Okay, so disc has no hole in it. Let me make that look more like no. Okay, no hole. And washers do have a hole in the middle of them. Okay, so it's whether your solid has a hole in it or not.